Okay, I'll hand your exams back at the end here. I need to post the answer key when I get back to the office, which I will. If you have any questions as you go over it, email me or come see me, and we can go over what you missed. All right. Any questions about any of today's reading or anything else? Okay, I'm gonna go through the example we left at the end of class on Friday, and then also this will kind of set up Wednesday, so when you go through Wednesday's material, it'll kind of be the same thing except a different case. So where we left off on Friday was we were going to take something like HCl and react it with this allylic alcohol. So we have the allylic alcohol here, and we're going to basically do an SN1 mechanism on it. So the first thing that we were going to do was to protonate the oxygen with the H+. My question is, which way does the arrow go? From oxygen to H+ or vice versa? Oxygen to H+. Okay, make sure you look, when you look at your exam, make sure that you're doing that, and if not, make sure you do it 2 weeks from today. Okay, because these arrows are still going in the wrong directions. They always go towards the positive charge. So in this case, the arrow will go like this, and I will end up with my oxonium ion. And then the next step is to lose the water. So I'm going to form H2O and then this allylic carbocation. Now, being an allylic carbocation, that has resonance structures. And so to write the resonance structure, I'm going to take this pair of electrons, move it here, so that I end up with the second resonance structure for that. Now, whenever you're doing these kinds of problems, I'm going to ask you, and my intent is to give you a take-home graded homework problem where you have to write some mechanisms out this week. Obviously not today, but probably on Wednesday. So I'm going to ask you to write the resonance hybrid. So when we write the resonance hybrid, we are basically doing what we do for transition states. We're going to average charges and we're going to average bonds. Now, there is sort of a pattern recognition you can do with this. And you could say, for instance, everywhere there's a plus charge in those resonance structures, there will be a delta plus charge in the hybrid. So there would be a delta plus charge here and a delta plus charge there. And that would be the average of plus, 1, and 0. So everywhere there's a plus charge, there can be a delta plus charge. Then averaging bonds, we're going to be in a situation where we have we've got, I don't like these dual screens because then I got to do it on both sides. We've got single, 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 double, single, double, double, single. So that means that the first bond is a single bond all the way around, and then partial double bond here, partial double bond there. So when you write the resonance hybrid for these structures, what you're going to find is that the dotted lines usually go in between the two delta positive charges. So if you're just, it's always better to go back to the basics and just average the structures out, but you'll see this pattern of the delta pluses and the partial bond. So that's the resonance hybrid, and I will always ask you to write that as well. Now, the issue is that the resonance hybrid is the true structure. But taking our Br minus and saying, well, I can add the Br minus to each of the two delta positive charges, you're like, where does the double bond go? So it's easier to just say, you know what, I know those two resonance structures aren't real structures, but let's react each of them with the Br minus. So that way I know where the double bond goes. So in this case, the Br minus would add to that carbocation, and the Br minus could come down here and add to that carbocation. Christian?
Using the Cl
yes. Probably should have been a little less harsh when people substituted that on their exams, and I wrote, where did the Cl come from? Too late now. That's as much as I said. Where did the Cl minus come from? So Cl minus is going to add to both of those. Again, those aren't the real structures, but it's easier to write it this way because then I know where the double bond goes. So that means that this product is going to have the Cl there, and then this product will have the Cl there. So I'm going to get two different products here. And potentially in the next chapter, we're in chapter 19 right now, the first part is dealing with allylic carbocations, and maybe we'll talk about allylic radicals on Wednesday as well because they're thrown in. So I got two different products. My next question is, which one's the major product? The answer is, it depends. It depends on what? Well, it depends on the reaction conditions. And so what that means, what it means it depends is that under one set of conditions, I can get this as the major product, and in changing the reaction conditions, I can then get that as the major product. This is not two different sets of conditions like Markovnikov, anti-Markovnikov. This is simply by changing those reaction conditions, I can switch what the major product is. So this is new. And so being new, we have to define some terms here. So what are the conditions first that can cause this reaction to switch? The first thing is going to be temperature and reaction time. So those are my two factors that I can change that will flip the reaction. It'll flip the major product. And so there's two sets of conditions here for each one. There's a high and a low temperature, and there's a short and a long reaction time. So what I'm going to say is that in terms of my temperature, I could use a high temperature and a long reaction time. And those two kind of go together. And then the other is to use a low temperature and a short reaction time. So those are my two sets of conditions. And I'm not going to mix and match. I'm not going to say short, high. No. It's either low, short, high, long. Because if I start mixing them up, and who knows what I'm going to get.
Doesn't raising the temperature usually make the reaction go faster?
Well, what I'm saying here is I can let the reaction go as long as I want. So what I'm saying is do the reaction at a high temperature, but then let it go like a day. A short reaction time might be like 15 minutes. And the temperature is going to depend, because room temperature might be a low or high temperature. If 70 degrees is my high temperature, then room temperature is a low temperature. If minus 80 degrees is my low temperature, then room temperature is high. So I usually don't put a temperature to this. I usually say it's either high or low, short or long. But we don't want to mix and match here because these two kind of go together, as you'll see when we explain or as I kind of go through the reaction coordinate diagram to explain what happens. And then for Wednesday, you'll see the same kind of reaction coordinate diagram for 1.2 and 1.4 edition, which is going to be virtually identical to this, except it's got an additional step. Okay, so these are our two sets of conditions. Okay. Right. Everybody with me so far? So these are given terms. The low temperature short reaction time is what's called kinetic conditions. The high temperature long reaction time is called thermodynamic. So the thermodynamic means that high temperature long reaction time, and then low and short is kinetic. So I could say, for instance, this reaction is going to be done under thermodynamic conditions, or it's going to be done under kinetic conditions. And that is how we switch the major product from being one to the other. The only question is, which is which? In this reaction, which one is the kinetic product that'll be favored by a low temperature short? Which is the thermodynamic product that'll be favored from a high temperature long reaction time? Okay. And so we have to go through that, and then why. So the issue here is I have two conflicting ways to determine what the major product is. In the past, what have we done to determine the major product? We've done one of two things, or we've done two of two things. Number one, we've said, okay, which product is more stable? Now, if I ask you which one of those two products is more stable, we need rules. Like, okay, what rule am I using? To my knowledge, we have never said anything about the stability of alkyl halides as products. Primary, secondary, tertiary, we never said, well, that one's more stable than this, because that's not a rule. There's no way to determine the stability of alkyl halides. So the alkyl halide part is irrelevant. What is important is this, the double bond. We have talked about what is a more stable or less stable double bond. The more stable double bond is the one that is more substituted. So in this case, we would say that the product on the right is the more stable product. And the product on the left is the less stable product. Again, we don't have rules for alkyl halides. And when I say that, we don't have rules for alkyl halide products. We have rules for free radical halogenation, but not in terms of products. As a matter of fact, the rules we use for free radical halogenation are basically the same rules we use for Markovnikov addition, which is the other way to determine what the major product is to look at the intermediates. Which intermediate is more stable? So again, in this case, I've got a double bond and a carbocation. I have to establish which one is the most important. And the most important part here is the carbocation. What type of carbocation it is. So the stability of the double bond is being outweighed by the stability of the carbocation. Meaning that the top carbocation here, the secondary carbocation, and the thing is it's secondary allylic, that would be the more stable intermediate. And the other one being a primary carbocation, primary allylic, would be less stable. But remember, the resonance hybrid is the real structure. So we're just using those to judge stability. So I would say that this is the more stable intermediate, and then the primary one is the less stable intermediate. Does that make sense to everybody? So then here's the issue. The issue is the more stable intermediate makes the less stable product, and the less stable intermediate makes the more stable product. So I got two things that are fighting each other. Which one wins? It depends. It depends on these reaction conditions as to which one I favor. Now, I don't think we did chapter 4 in Top Hat last semester, but if we did, they had a brief discussion about this with energy diagrams that kind of were fighting each other. What happens if the less stable product comes from the more stable intermediate and vice versa? So we didn't talk about that. Even if we had, you would have been like, that's chapter 4. How do I remember that? Hopefully you still kind of remember it, but that's foreshadowing 15 chapters in advance. Probably not going to be all that successful. But that's where they kind of talked about this. So if you want more details, you can go back to chapter 4. But this is our problem. The problem is, so which one predominates? It depends. So let's draw out the energy coordinate diagram and talk about how we can rationalize or how we can figure out which one is going to predominate under which set of conditions. Unfortunately, to do this, I have to start with the resonance hybrid in my reaction coordinate diagram. So here is my reaction coordinate diagram. I'm going to start in the middle. And let's see, we're doing Cl, so I'm going to add the Cl minus. To both of those delta positive carbons. So if I add the Cl minus to the primary, the one that's delta positive but as a primary carbon, I'm going to go to the right. If I add it to the middle carbon, I'm going to go to the left. So I'm kind of sitting in a valley and I can go this way or I can go this way. So let's map out what those two hills look like. And more importantly, what's on the other side of the hill. So my first question would be, I need to draw transition state energies. So which one of these two additions, left going to the right by adding primary, going to the left by adding to the secondary, which one of those is going to have the lowest transition state energy? Take a minute and discuss. Which one of those two is going to have the lowest transition state energy?
That's what I was going to say. I was going to say the more Sure, yeah. I'm going to go back. She's actually always here.
Okay, sounds like our discussion got really loud, and then it went to nothing, and now we're talking about non-chemistry related stuff. Which is a good time to ask. Okay, let us call primary, secondary, number 1 or 2. So my question is, by your finger, is the the chlorine adding to the primary carbon or the secondary carbon going to produce the lower, more stable transition state? What do you think? Which one are we adding to form the more stable transition state? 1 or 2? Okay, I see some 2s. I saw some 1s. All right, give me a case for number 2.
mean, if it's like more stable, then it would probably be easier to form, and like chemistry likes to go the easy way, so when they do that,
Not all chemistry likes to take the easy way.
what we've learned sometimes too.
Right. So you're saying the secondary more stable? Except in this case, I wouldn't say it's more stable. What would we say about the secondary position?
More substitute.
Yes. I'm having a sense of deja vu. The topic is epoxides. How do we rationalize the epoxides in the triangular intermediate? What did we say about the more substituted carbon in an epoxide? It had a greater delta positive charge. So that's the way I would say it. I would say the secondary has a greater delta positive charge, and the primary, less positive charge. Why would you give me the case for the primary then? What's a rationale for choosing primary? Somebody had a number one finger up. Does that mean we're backing off number one? No. Have I humiliated anybody that's given the wrong answer yet today?
I'm for the secondary case, but like could it be similar with the oxides, like that it's more basic conditions, so we want to go to the less substituted.
You're almost there. I'm hearing the word.
Basic?
No.
Oh.
You haven't gotten to the word yet.
I want to go to the less substituted carbon.
Which is going to be
More negative.
sterics.
Less negative.
So just like in the epoxide case, these both have a significant charge to them, so sterics doesn't play a role. But if I had to guess, I would think sterics would come up somewhere in the discussion. It is not. Just like the epoxides, what's going to make the chloride want to go to the secondary position and form a more stable transition state is because that carbon's going to have a greater delta positive charge. So if you think about it this way, the transition state's going to have a -1 and a delta positive charge. That transition state's going to be more stable if I can get those -1 and the delta positive as close together as possible. Whereas in the primary case, it's not going to have all that much delta positive charge. And the secondary isn't going to be fully +1, but it'll be closer than the primary. So that means we won't have as much extra charge in the transition state. So when we go this way, it's a lower transition state energy than if we go that way. Okay, so the less stable transition state is going to be with the primary. The more stable transition state is with the secondary. Why is that important? What is this? Those are the activation energies. How does that activation energy help us with the major product? Arrhenius equation says rate equals A times e to the minus EA over RT. So the Arrhenius equation gives us the relationship between activation energy and temperature and rate, which is what you learned in general chemistry. The lower the activation energy, the faster the reaction. So therefore, which way is this reaction going to go initially? If I stop the reaction after 5 minutes, what am I going to have more product of? Left or right? Left. Why? Lower activation energy. Okay. And what product am I producing when I go to the left? When I go to the left, I'm producing this product. When I go to the right, I'm producing that product. We have a problem. So this explains how the product from the more stable intermediate would be considered to be the kinetic product, the one that's formed the fastest. And that's what kinetic product means. It's going to be the one that forms the fastest. Why does it form from the more stable intermediate? Because technically that's the one that has the lower transition state energy. So I'm going to form the left product much faster than I'm going to form the right product. And I can change that difference by doing what? Starving the birds. Right? I'm in a valley, I need to go over 2 mountains. This is where we can talk about birds and hikers and energy. If the birds are starved for energy, they're going to make it over the left, crash into the mountain on the right. Well, it's better than the hikers dying on the mountain, right? And if the birds have a lot of energy, what happens? They can go over, but how fast are they going to go over the big mountain? What's the best I can do here? If I give the molecules all the energy they need, what's the best I can do? Same rate, 50-50. So from looking at just the transition states, the best I can do is 50-50. If I give the molecules a lot of energy. So there's our low temperature. Favor the product on the left. High temperature really would give me 50-50. That's not what happens. What happens is I completely reverse it and I make the product on the right as the major product. So I'm missing something here. Everybody see my dilemma? I can explain kinetic, but I can't explain thermodynamic. Because 50-50 is not a major product. So now let's draw in the other parts. Which of these 2 products is more stable? Left or right? Right. So let me draw in my diagram here. So there's my energy of that product. And let me draw in my energy here and make it significantly lower. Now, how does this play into that? Well, here's the new wrinkle. In all the reactions we've kind of done before, you could never have this happen. What's this? That's this. I can lose the chlorine off both those molecules. And what's going to happen? I'm going to end up back at my resonance intermediate. So these reactions are reversible. And that's new. We haven't done that in the past. So now I've got a reversible reaction. Now if I look at the reversible reaction, I've got 2 more sets of activation energies. Right? Because now going in the reverse, I've got this activation energy, and over here, I've got that activation energy. So if I'm sitting on the left, if I'm sitting on the left here and I want to go back to the middle, I've got to undergo the left activation energy in reverse. If I'm sitting over here on the right and I want to go backwards, I've got to overcome a bigger activation barrier. So what happens? let's do kinetic conditions first. Under kinetic conditions, I've got a short reaction time and a low temperature. My reaction starts out here. It goes over the small barrier if I give it just enough energy to do that. It goes over the small barrier more than the large barrier. The molecules end up over here. I didn't give them enough energy to reverse, so most of the product is here. And if I shut the reaction off after 5 or 10 minutes, they're all stuck there. So kinetic conditions are going to favor the product that came from the more stable intermediate. Does that make sense? So we would call that the kinetic product. But now let's go to thermodynamic conditions. Long time, high temperature. What happens initially? Initially with the high temperature, more end up over here than end up over here because simply this barrier going to the product is lower than the barrier over here. So initially I end up with a lot of product here, but I'm not stopping the reaction, I'm letting it go. What happens? I got a lot of extra energy, this can reverse and come back here. And then it might go there again, then come back here, and it might go there again. But if it comes back here and it goes over there, over the right-hand barrier, then what happens? Now I'm kind of stuck in this well where it's going to be difficult for me to get out of it. So if I give the reaction enough energy and enough time, what happens to the products? They mostly end up on the right-hand side, stuck in the well. That would be the thermodynamic product. The thermodynamic product is the most stable product. So by adjusting the reaction conditions and looking at this kind of diagram, I can adjust what the major product is. But the thing that's new about this is the reversibility of those second steps. You might say, but wait, we had carbocations when we did like Markovnikov addition. Yeah, and we made a single bond with a chloride attached to it. I suppose that chloride could have left, but we didn't say that at the time. That's going to be more difficult. Here, I'm forming a resonance-stable intermediate, so it's possible for it to reverse itself. So that's how we can explain the kinetic and thermodynamic. So the kinetic product is the one that comes from the more stable intermediate, and the thermodynamic product comes from the more stable product. The kinetic product is favored under short reaction times, low temperature. The thermodynamic product is favored under high temperature, long reaction. And that's how we would explain how we can switch between the two of these. There's lots of kinetic versus thermodynamic systems out there. Does that make sense? So if I gave you one of these molecules to write the full mechanism of, the whole problem would be write the mechanism, write the resonance hybrid, write all the resonance structures, and then identify the kinetic and the thermodynamic product. You have to determine the kinetic and thermodynamic product for each individual reaction by using the most stable intermediate versus the most stable product. So you don't have a choice. And it may vary. You're going to see that for Wednesday we can do what's called 1-2 and 1-4 addition. I will quickly show you on Wednesday that the 1-2 product could either be thermodynamic or kinetic. The other one could be thermodynamic or kinetic, so there's no way to save the room up here to remember, well, this is this, because this isn't always that. You've got to take them one at a time. Remember up here, what the basics are. Most stable intermediate, kinetic, most stable product, thermodynamic. That will be the quiz. That will be part of the quiz on Wednesday. I will say thermodynamic product, this temperature, this time. High, low, short, long. And then maybe identifying the kinetic and thermodynamic products of a reaction. So how would we do that? We would say, let's say, I had that reaction. I'm going to do water. I'm going to add water to it. So the chloride's going to come off. I'm going to make my two resonance stabilized carbocation resonance structures, and then I'm going to add the water to each. So that means I'm going to form that as my first resonance structure. That as my second resonance structure. Add water to each. In 2 steps. The water adding the entire water molecule and then losing the H+. I'm going to end up with these two products.
Is there an arrow pointing from the double bond to the carbocation on the left one?
Because that's showing how we move the pair of electrons to form the second resonance structure.
Oh,
That's the arrow to form the
okay.
resonance structure. I could put a small arrow here, basically doing the same thing. So if I said, which one of these two products is the thermodynamic product? Which one is the kinetic product? First of all, if I gave you this reaction, I might say write the kinetic product here, write the thermodynamic product there. You'd have to identify the two products, probably knowing what carbocation they come from in order to completely answer the question. So in this case, which one is the thermodynamic product? The one on the left or the one on the right? Left? Do we agree with that? Because it's coming from the least stable intermediate or the more stable product. I would remember most stable product. And then the kinetic product is the one on the right. So you'd have to write the intermediates out and then write the products out. If I'm going to ask you to do this on Wednesday, which I probably should, at least for Wednesday, I might write all of this stuff out and say which one's a kinetic product, which one's a thermodynamic product, just to make sure you got it. And then I will check to see that you can write all that stuff in a graded homework problem. But I don't ask for mechanisms at the beginning of class because it's that short. The mechanisms sometimes are not very short. Now, if you're asking yourself the question, are there reactions that don't have a kinetic and thermodynamic product? Maybe they're the same. Well, number one, if you do a reaction that gives you the same product, whether it's for both resonance structures, there is no kinetic and thermodynamic product. There's uno product, and that isn't kinetic and thermodynamic. If you were to have resonance structures that were both secondary, or both tertiary. You would get a 50-50 mixture, which means I can't switch because the intermediates have the same stability. And so if you had that situation, and I'll link up this morning's lecture because that was like the last 5 minutes of class. If you wanted to see examples of those, they were really quick. Okay, I could do something to that molecule and make it not have a kinetic and thermodynamic product. The thing I would do is I would actually add another methyl group to the carbon with the chlorine, so they're both secondary carbocations. And if I wanted to make it one product and one product only, erase the methyl group and put the chlorine in the allyl position. So there are cases, they're rare, and I'm not going to necessarily ask you for these right off the beginning, but there are cases where you wouldn't get thermodynamic and kinetic products because the carbocations would be the same in the two resin structures, or you would be making the same product. Everybody likes exceptions because, quite honestly, it's the exceptions that make good exam questions. But I'm giving you the exceptions to those so we can do that. So for Wednesday, I'll post some practice problems today, writing through the mechanism, identifying the products for Wednesday. But on Wednesday, I'll ask the question of what goes with kinetic, what goes with thermodynamic in terms of conditions, and I'll probably give you a reaction like this and say which one is kinetic and which one is thermodynamic. Everybody should get 10 out of 10, right? And then we'll make the other problems a little bit more difficult. Okay, so I will post the answer key for this exam after